Hello everyone, in this lecture we're going to continue talking about counting principle, more specifically on permutations. So a permutation is an order arrangement of n distinct objects. So there are two requirements for this setup. The first one is that no object can be selected more than once, and the second condition we need to impose is that the order of the arrangement matters. So no object can be selected more than once, and order of arrangements matter. So that's the requirement for permutations. Let's take a look at the following example. Let's say you have a set S with the element of A, B, and C, and you want to know how many permutations you can form from this set S. So in other words, how many ways that you can arrange the three-letter A, B, C. So because you only have three letters in this case, so it could be easy enough to write out all the possibility of the arrangements. For instance, you're going to have the arrangement of A, B, C, and then A, C, B, or you can have B, A, C, B, C, A, C, A, B, and C, B, A. So there are 6 possibility of arrangements for this particular set, or there are 6 permutations of S. Even though this contains the same letters, A and B and C, the positions of the letters are different, and therefore you're going to have a different outcome for this setup, since the order of arrangements matter. But in practice, the set that you're dealing with may have a lot more elements in it. In those cases, it's really hard to list out all the permutations of the set. So what can we do about that? So let's consider the following example, and from that example, we're going to come up with the formula for the permutations of a set of n distinct elements. So let's move on to the next example. So in this example, we want to know how many permutations that we can form from the set of the elements of A, B, C, D, E, and F. So there are 6 letters in the set. So we're going to follow the idea from the counting principle we learned from last video, that is multiplication principle. So let's say you have 6 different spots here, or 6 different slots. So there are going to be 6 choices for the first entry, or the first slot. And remember the setup for the permutations that we're working with, that no object can be selected more than once. So because we already selected one of the 6 choices here, we're left with 5 other choices for the next slot. So this is 5, and then so on and so forth. Because you already choose 2 different choices here for the first 2 slots, you only have 4 letters left for the 3rd slot. So there's only 4 choices here, and for the next slot, you only have 3 choices, and here you have 2 choices, and then 1 choice. And the permutations of the set S is going to be 6 times 5 times 4 times 3 times 2 times 1, and this is going to be equal to 120 permutations, or there's 120 different ways to arrange the 6 letters into 6 different spots. In mathematics, there's a shorthand notation to represent this type of calculations, because this is the product of all positive integers from 1 to 6. The notation is going to be 6 factorial. So in general, the factorial is going to be, so n factorial is going to be equal to 1 times 2 times 3 times n minus 1, then times n. So n factorial is the product of all positive integers from 1 to n. And therefore, when we deal with permutations of n distinct objects, the formula for that is going to be, there are n factorial permutations of n distinct objects. So when we talk about permutations of n distinct objects or element, we have that there are n factorial permutations of n distinct object or element. Now let's move on to one more example related to permutations of n distinct objects. In this example, the question is how many ways can you arrange 5 different books on a bookshelf? So this is similar to the idea of permutations of 5 distinct elements. Right, so you have 5 different slots on the bookshelf here. For the first slot, you have 5 different choices of book, and then you're left with only 4 choices for the next slot, then 3, then 2, then 1. So this is 5 times 4 times 3 times 2 times 1. This is equal to 5 factorial, or 120 different ways for you to arrange 5 different books on the bookshelf. Now, with this similar example, I want to move on to the next example and consider the case where the bookshelf only have a number of slots that is less than the number of books. So let's set up the questions. That is, I want to know how many ways that we can arrange 5 different books to 3 slots on a bookshelf. So remember, in this case, we only have 1, 2, and 3 slots. So for the first slot, there are 5 different choices. For the second slot, you only have 4 different choices of book. And for the last slot, there's only 3 different choices. So you do multiplications now, and that's going to give you 60 different ways that you can arrange 5 different books to 3 slots on the bookshelf. And I want to take a little bit of work here, a little bit of algebraic manipulations to arrive at a formula that I'm going to give later. So the setup of 5 times 4 times 3 can be written as 5 times 4 times 3 times 2 times 1. So technically what you see here is I multiply the 2 new numbers, 2 and 1. But because it's coming out of nowhere, so I need to technically divide by the same number, that is 2 times 1. So we can cancel this out and come back at 5 times 4 times 3. So technically, I didn't make up any wrong calculations at all. So by doing this particular setup, I want to arrive at the formula that I'm going to give you later. So on the numerator, I have 5 factorial. And in the denominator, I have 2 factorial. And when you do this calculations, you're going to have 120 divided by 2 is going to give you 60 different ways to arrange 5 different books to 3 slots on a bookshelf. Okay, so this formula right here is called the K permutations, or depends on the textbook that you read. It's also called R permutations. For N is the total number of available objects, and K or R is the number of positions or selections. So that is the next thing I want to give you, is called the K permutations. And the notation for that is P of N, comma K, or you can have R permutations. The notations is P of N, comma R. So either one should be fine. In this case, N is going to be the total number of available objects, and K or R is the number of positions. Or selections. For K permutations or R permutations, the formula is going to be P of N, comma K is equal to the fractions of N factorial over N minus K factorial. So this say that we arrange K objects chosen from N distinct objects. Alright. And we're going to consider applying this particular formula in the next couple of examples. So the next example is going to be, there are 8 runners in a race. The first place gets a gold medal, the second place winner gets a silver medal, and the third place finisher gets a bronze medal. We want to know how many different ways are there to award these medals. So for this problem, you can see the total number of available elements in the set is going to be equal to 8. So N is equal to 8. And the number of positions or selections that we have here is K equal to 3. For this example, the orders really matters, right? Because you need to have the first place, then the second place, and then the third place, right? And with k equal to 3, we can say that the problem we are dealing with is 3 permutations. So given n equal to 8 and k equal to 3, we can set up p of 8, comma 3 equal to 8 factorial divided by 8 minus 3 factorial, or 8 factorial divided by 5 factorial. And if you use a calculator, you're going to arrive at the answer, and that's going to be 336 weights. So in doing this, we conclude that there are 336 different ways to award those medals. Now we're going to move on to the last example related to permutations. So in a company, we want to know how many ways that we can select a chairperson's, vice chairperson, secretary, and treasurer from a group of 10 persons. So the big assumptions here is obviously we cannot select a person for more than one positions, and the order of arrangements matters. That is, you need to have one person for the chairperson, so one person for the vice chairpersons, one person for secretary, and one person for the treasurer. Another practical assumption is that all of these 10 persons are going to have similar qualities for the choices that we're going to make. So 10 persons in the company, and we're going to choose a chair, a vice chair, a secretary, and a treasurer. So from here, this line, we can deduce that n is equal to 10, and from this line, we can see that k is equal to 4. So we have a first pick to be a chairpersons, the second pick to be a vice chairpersons, the third pick to be a secretary, and the last pick to be a treasurer. Therefore, this is going to be a 4 permutations. And you do p of 10 comma 4 is equal to 10 factorial divided by 10 minus 4 factorial is equal to 10 factorial over 6 factorial. Using the calculator, we arrive at the answer of 5,040. So there are 5,040 different ways to select a chairperson's, vice chairperson, secretary, and treasurer from a group of 10. And that's it for the example. I want to recap what we just learned about permutations. In permutations, different order are considered to have different outcomes. In permutations is used mostly in the concepts of arrays where you have a defined winners. Right? The first place get gold medal, the second place get a silver medal, and the third place get the bronze medal. Or in a company, when you want to choose a job title, a positions, a rank, so the orders really matters, right? So, in a company, you need to have, let's say, presidents, the vice president, a treasurer, and any other positions with ranking. And in those situations, again, permutations will be used to do the calculations. So that's it for me. We're going to move on to the next video where we talk about combinations.